Hi, this video is part of a course on food physics. The Porous Media framework is part of the theory section of the course. The subsection for this particular video belongs to the governing equations for transport. And so we're here now, and the immediately preceding video discussed the mass transport equations, and the immediate following video would summarize both heat and mass transport processes. So similar to mass transport, the governing equation for heat transfer is derived by combining the conservation of energy and the rate laws. So the rate law that we need here is Fourier's law for heat conduction plus the flux due to transport of the fluid species. That is transport of water, vapor, air inside the porous media. So by combining these, we get the governing equation for heat transfer. So the conservation of energy written in this familiar form is written for a system defined with a boundary. So what's coming into the system minus what's going out, in minus out, plus what is generated. So the meaning of generation is conversion from any other kind of energy into thermal energy. A typical example would be, let's say, microwave heating. So it's converting electromagnetic energy into thermal energy. So as far as the thermal energy balance is concerned, this is really thermal energy balance. Thermal energy balance is concerned, then we are generating heat. Microwaves are, because of microwaves, heat is being generated. So all that, what's coming in minus out plus generation, leads to change in energy stored. So this is the most familiar form of um, uh, writing energy conservation or thermal energy conservation. So as we have done for mass, all the different mechanisms of heat transfer can be seen as belonging to two groups, diffusion or diffusion-like, and that will be the heat conduction in case of heat, and convection or due to movement. So movement would be the heat carried by the fluid transport. Now remember, the transport is of fluid involves both diffusive type movement of the flow of the fluid and also flow of the fluid. Both are included in transport. Like we did for mass, we're going to first develop the heat equation by doing energy balance on a simple system, like, let's say, single phase system like water, not in a porous media, but just water. How does heat transport? So to do that, we're going to do a control volume analysis. And so if this is my water, let's say, and I choose a small volume that is fixed in space, the control volume, which is shown enlarged here. So it's a size delta x, delta y, delta z. And on this control volume, we look at how energy can come in and go out. So energy can come in by conduction, which is given by this Fourier's law, and also it can leave by conduction. It can leave by conduction. So the other mode, the other way that energy can come into this control volume is by bulk flow. So bulk flow, the flux due to bulk flow, as we have derived earlier, is U times rho times Cp times T minus Tr, where Tr is simply a reference temperature that will get cancelled out later on anyway. And heat going out by bulk flow is also the same thing but evaluated at x plus delta x. So we keep talking about these two groups of transport modes. One is diffusive type. So this conduction we just did was diffusive type, and the other one is bulk flow, and together we have the total flux. So this is the total flux of heat or thermal energy, and this is also the total flux of thermal energy going out in a very simple system, not porous media yet. So in that simple system, we could also have heat generation. So heat generation could come from, let's say, if this is being heated in microwave, so then thermal energy is generated. It's converted from electromagnetic into thermal energy. So what we will do now is, just like we did for mass, we're going to do a conservation of energy. This is conservation of energy written in word form. What's coming into the control volume minus what's going out plus what is generated would be equal to the change in storage. So now let's look at these terms individually. How much energy came in over time delta t? So I'm going to do this balance over time delta t. Okay, so over time delta t, how much energy came in? I'll do that in joules. Okay, so the conductive flux is minus k del t del x at x, and plus the flux due to flow. This is the amount of heat that is simply being carried into the control volume. So because water can flow, it is simply this energy is simply being carried into the control volume. So there's two parts. Even if the water was still, there will be the conductive flux, and if the water is moving, then it's carrying some energy with it that's on top of the conductive flux. So these two are added, and their units are in watts per meter square, meaning joules per meter square per second. So we have to multiply by the area through which they're coming in. That's delta y times delta z. That's the area through which they are coming in, and so that is meter square. So that gives me watts, and then delta t is seconds. So when multiplied, I get joules. Okay, so that's what is coming in, and then what is going out. What is going out is the same quantity, is exact same quantity, but evaluated at x plus delta x. Evaluated at, so it's the same quantity evaluated on this face. And now the energy generated. So the generation Q, if I define it as watts per meter cube, which is also joules per meter cube per second, then the joules that are generated over time delta t is given by Q multiplied by the volume delta x, delta y, delta z times delta t. And finally, because of this energy coming in, going out, energy generated, there's going to be change in the storage of energy in this control volume. So change in energy storage in the control volume here. So change in energy, if so in other words, the control volume will change its temperature. So if it increases temperature, it's storing more energy. If it decreases temperature, it stores less energy. So this change in energy of the change in thermal energy of that control volume is given by mCp delta T, mass times its specific heat times change in temperature. So mass of that control volume is its volume times density. So that times the specific heat times delta T is the change in storage. So we put all this together, and we get this equation. And after we put all this together, we divide throughout by delta x, delta y, delta z, delta t, so it looks a bit simplified. And I have rearranged this a little bit, putting in x plus delta x first and x next. Why? Because then if I let delta x, delta y, delta z go to delta t go to 0, so if delta x goes to 0, then the first term is a function evaluated at x plus delta x minus the same function evaluated at x divided by delta x. So if I take the limit delta x go to 0, then this is the derivative. So del x is the derivative of minus k del t del x. And then the next part is going to be del x, because this is the quantity at delta x minus the quantity at x divided by delta x, with delta x going to 0. So it's the derivative of this whole thing. Notice that tr has been dropped out because tr is a constant, and we're writing this as a derivative, so we do not need to keep the constant. If you keep the constant, then that term, when you take the derivative, it will be 0. Okay, plus q, and then rho Cp stays as is, and del T becomes the partial derivative of temperature with respect to time. And now we have to use continuity. What is continuity? So you notice this term here, suppose we consider rho Cp to be constant, then the term looks like this: del x of ut. So that is equal to u del t del x plus t del u del x. Now notice that in our control volume, if we think of the velocity coming in, so velocity, let's say this is my x and this is x plus delta x. So the velocity at x and velocity at x plus delta x, is there a relation between them? So the point is, if this is a constant density system, if the density is not changing, then we can easily find this relation, because A times ux is the volume, that is the rate at which volume flow is happening. In other words, this is the volumetric flow. If we multiply by rho, then it's the mass flow coming in. And likewise on this side, rho A u x plus delta x, let me rewrite this, rho A u x plus delta x is the mass flow going out of the control volume. So this is what is going out, and what's coming in is rho A u x, what's coming in. So the mass flow has to be the same unless we allow mass to be accumulated, which means it's more like a compressible system. So we're not allowing that. So then the mass coming in should be equal to mass going out. And if it is constant density system, as we just said, then ux is equal to ux plus delta x. In other words, if we write it in terms of derivative, ux plus delta x minus ux equal to 0 divided by delta x equal to 0. So with delta x going to 0, this is written as del u del x equal to 0. So this term cancels out. So if that happens, then back to this term here, we can simplify it further. So we can simply write, we can take u out. So we took u out, not because u is a constant, but there is the mass balance, or the use of the continuity equation, and the density is constant. So we took u out, and then the term looks like this. And so we're almost done with simplifying. So this is the final version. We took the Cp out, so it's u rho Cp del T del x plus Q equal to rho Cp del T del T. So let's make sure we understand. So we understand the physics that they stand for. So this term stands for conduction. This term, because it has the u, and if you can go back where it came from, this guy, this is due to flow, and then this guy is due to generation, and this is the effect. The net effect is the change in storage. So you see, we are staying completely mechanistic in this process, and this is my final heat equation. But remember, this is for a very simple system. This is for just, let's say, heat transfer in pure liquid in a very simple system. We're going to extend this to porous media. So the last equation in the previous slide was actually extending it to more than one dimension. We did that energy balance in just one dimension, and the very last equation, it extends it to multiple dimension. Now we want to extend this to multi-phase situation, and we're going to do that in somewhat ad hoc way, in a very simple way, without getting into a lot of the mathematical details. So the single phase equation, or heat transfer in single phase, that we derived looks like this one. We're going to extend this one to multi-phase porous situation, we're going to do that informally, but let's try to keep the meaning of the terms clear in our mind so that this extension is kind of nice and smooth. So the equation that we derived for 1D for single phase was this equation. If I look at the term U times rho, if I look at the term U times rho, U has the unit meter per second and rho has the unit kg per meter cube. So this is the unit for this term is kg per meter square per second. So that is really, we can think of that as the mass flux of that phase. It was single phase, so there is only one term. So when I extend this equation for porous media, water is going to be just one of the phases. So let's write it for the water phase. So now I am rewriting that same equation on the left. So rho Cp is that of water, and here the mass flux of the phase, we now have mass flux of just water, and I'm calling that as NWX because the mass flux of water can be due to multiple mechanisms. Then the Cp is also for water. Notice it's the same temperature. So we're going to talk again later, but in the multiphase situation in a porous media at any location, all phases share the same temperature. So temperature in solid, liquid, gas, they're all the same at one location. So the temperature is the same. So now K, thermal conductivity, is that of the water. And now to use this in a porous media situation where we can have evaporation, we need this latent heat term, latent heat of evaporation, plus the energy generation like we discussed for microwaves and so on. So now this is for one phase, and in this case it's for water in a multiphase situation, in a multiphase porous media. So we're going to now build the various terms. So in extending to the porous media, where we have a solid matrix and the various fluid phases, water and vapor and air, we're going to first consider the conduction term. So remember, conduction happens, of course, through each one of the phases. So conduction happens through the solid phase, through the gas phase, and through the water phase. So they all need to be considered. So let's see how we can do that. So we replace the conductivity term. So let's say for one phase we have this equation, right? This is the conduction term for, let's say, water phase that we just derived, where we have the thermal conductivity of water. When we have multiple phases, we would replace the term to a volumetrically averaged thermal conductivity of all the phases. So volumetrically averaged thermal conductivity of all the phases. So we are including all of the phases explicitly, and that volumetric averaging is shown here. So if you take a phase, so let's say the solid phase, how much solid phase is there? It's the volume fraction of solid. If phi is the porosity, then that's the total porosity, then 1 minus phi is the fraction of solid. Total porosity includes a porosity due to liquid or gas phase. So when we take out liquid and gas, it's just the solid. So 1 minus phi times that. Then phi, the volume fraction of non-solid, that's liquid plus gas, multiplied by the liquid and the gas part, but they also need to be weighted because they're not in equal amount. So it's Kw, the thermal conductivity for water, times the saturation of water, which is the volume fraction of water in the porous part. So volume of water divided by volume of water plus volume of gas. And so likewise, this is the saturation of gas multiplied by the gas portion. So the gas portion again is, there is vapor and there is air. So we multiply the vapor part by its mass fraction and then the air by its mass fraction. So you see, altogether we have this K effective, that is a volume averaged thermal conductivity that is going to be used, and that takes care of conduction through all phases: solid, water, vapor, and air. So now the convection term. Note that the convection, or the flow carrying energy, occurs due to movement of all the fluid phases: water, vapor, and air. So let's look at them. So this is the porous media with the water and the gas phase in it, and they are flowing. So convection can be from that of water or from the gas, and they both need to be considered. So let's see how we do that. The convection term, when we wrote it for single phase, one phase, remember it was mass flux of water times the rest of the terms, the specific heat and the temperature gradient. This is for one phase, water phase. Now we want to include all of the phases, water, vapor, and air. So it will be all the energy carried by water, energy carried by vapor, and energy carried by the air. And so each one has their mass flux. Each one has its mass flux multiplied by the specific heat of that phase. So in this case vapor, and in this case air. Okay, now a very important part. So this is the NW or NV. These are the total mass fluxes. So mass flux, remember, mass flux is also due to two groups of mechanisms: diffusion type and flow type. Okay, so we have to include both of them in the mass flux. So let's see the first example. Mass flux of water has mass flux due to flow, the velocity due to pressure driven flow, or mass flux due to diffusion type movement, which for water it's the capillarity. So likewise for vapor, it is again pressure driven flow. Let me remove this one. Yeah, it's the pressure driven flow, and then the binary diffusion in air. So one part is due to flow, other part is due to diffusion. As long as they are moving, they're carrying energy with it, so they both need to be included in this flux term in my convective heat, the convection term. And finally, just like vapor, so we have the air flux is going to be due to pressure driven flow or binary diffusion in air. In this case it would be vapor. So air in vapor. So there is a diffusion part and there is the flow part. They both need to be included in this mass flux. So this now gives me the convection term in my heat equation due to all the phases together. All of the energy that's being carried because fluid is moving is now included in the porous media. And now for the remaining terms, transient and generation for all the phases. So for the single phase water, the transient term was written as rho Cp for water times del T del T. When we want to include all the phases, then we write rho effective for all the phases. So how do we get this rho Cp effective for all the phases? So notice that rho Cp, what is the unit? Kg per meter cube multiplied by joules per kilogram per degrees Kelvin. So this is joules per meter cube. So this rho Cp is volumetric capacity and it's in joules per meter cube. So the effective volumetric capacity, volumetric heat capacity is going to be volume weighted average for all the phases. So this is what it's going to look like. I'm going to delete this part now. And the volumetric average is rho Cp effective equal to, okay, what fraction is solid times rho Cp of solid, and phi being the porosity. And so 1 minus phi then is the volume fraction of solid, plus phi volume fraction or the volume fraction of the pores multiplied by the saturation of water. That's the volume fraction of water. Together, they're the volume fraction of water multiplied by the volumetric heat capacity of water. And in the same way, phi times Sg is the volumetric, the volume fraction of gas multiplied by the volumetric capacity of the gas. So for gas, again, it's made up of vapor and air. So this is the density of gas, and then between vapor and air, again, the heat capacity is weighted by the mass fraction in this case. So this is the composite heat capacity for the gas times the density of the gas and times, of course, the volume fraction of the gas. So that's how we're going to get the rho Cp effective. For the generation term, for one phase, it will be, if it is just water, then how much is, let's say, microwaves are absorbed in water alone. So if we think in the context of microwave heating, then the term for water would only have the microwave absorption for water. For all the phases together, then its microwave absorption averaged over all phases. So heat absorption in each one of the phases, solid and liquid, typically we ignore microwave absorption in gases, but so it's solid and liquid weighted together. So these are discussions that are part of a different physics. So if we're doing microwave heating, then it will be in the microwave module. So the point is the heat generation term Q is going to have the combined heat generation for all the phases. So putting all the terms together, let's say for 1D, so that it's easy to see, we have the storage term or the transient term that has the rho Cp effective. Then we have the convective term that has the convective transport by each of the phases. So energy carried by each of the phases, where NWX is the flux of, or in this case, it's the flux of the water phase. Remember, this flux includes flow plus diffusion. So diffusion in case of water, of course, would be capillarity, and likewise for the other phases. So the flux term is not just flow, it's transport, it's flow plus the diffusion. And then the heat conduction term, conductive transport term, where you have a K effective, or the effective thermal conductivity for all the phases combined as just described earlier, plus we have heat generation Q, and we have the sink term or the negative generation term due to evaporation, because evaporation takes away the energy as due to conversion from liquid water to vapor. The equation below that just popped in is the generalized form. So whereas the top one is for 1D, and then this one is a more general version, but you see it's the same stuff. We have the flux in the general form and times the specific heat and so on. So really nothing else changes, no meaning changes. It's just written more generally. So that is the entire combined the entire heat equation that has all of the terms together. I want to remind us that even though there are a number of phases, there's the solid, there is liquid, the water, there's vapor, air, there's so many phases, but there is only one energy equation for temperature. There is no two equations in our formulation. So at any point, at any location, there is only one temperature that is shared by the solid, liquid, gases, and so on. So at any point, there is only one temperature. This is known as the local thermal equilibrium assumption. It doesn't have to be true all the time, but it's mostly true, and it is the most common assumption that we make. So there is only one energy equation for the entire system. And so this governing energy equation then would be solved to obtain the temperature T over the entire domain and with time. So I will repeat now what we have already said in one or two different ways. just so that we are more clear about things. So the first one, this is a graphical representation of what we just did. The conductive flux, the heat conduction in the process, it happens in solid, in water, vapor, and air. So we include all of the heat conduction through a volume weighted average when we use Fourier's law. So volume weighted average of the thermal conduction. Likewise, for convection or flow and diffusion related heat transport. So the convection term, that is due to the transport of water, vapor, and air in the matrix. And by transport, I mean both flow and diffusion like movement for each one of the phases. So flow could be due to pressures, and diffusion like movement could be capillarity or molecular diffusion, as the case may be. So this flow and diffusion related heat fluxes are all added together. So the heat carried by each one of them, water, vapor, and air, are added. And then in the source term or generation term, we have the composite heat source. So let's say it's microwave heating, then the heat generated is going to be some sort of a average, volume averaged over all the phases. And evaporation also is going to be defined as per unit volume, and so the heat contribution of evaporation would be the latent heat times the rate of evaporation, and that's kind of a negative generation term that shows up. So that's what makes up the generation term. And finally, the change in storage. So because of the conduction and heat carried by flow and diffusion, because of generation terms, there's going to be change in storage, and that change in storage happens in solid, in water, in vapor, in air. And the way we're going to include all of them is a volume weighted, it's a volume weighted average of heat capacity times the density. Volume weighted average of heat capacity and density, or the volumetric heat capacity weighted by volume of each one of the phases. So that's the big picture. Looking at it another way, the total heat transport has a diffusion-like component, that is the heat conduction, and that is averaged over the four phases: the solid matrix, liquid, water, water vapor, and air. And the heat transport has a convection or a movement related term, a transport related term. And so that is the heat carried by all the fluids in there, like water vapor, like air, and its transport. So it has two parts: flow and diffusion like movement of the fluid. So before we finish up the heat equation, just a few comments relating it to other types of physics and therefore other modules. So the Q term in the heat transport equation is the heat source term, and heat source simply means its conversion from other types of energy into thermal energy. This can happen, for example, in microwaves, where electromagnetic energy is converted into thermal energy. Likewise, for radio frequency, it does not always have to be electromagnetic energy to thermal energy. It can be mechanical energy into thermal energy, like in ultrasound and high pressure. So in all of these physics, the physics will provide information on Q. So it will typically provide an expression for Q as a function of the parameters of that heating. Let's say for microwaves, then it will be electric field and dielectric properties and so on. So that computation would be then included in this. Otherwise, in other words, that physics would be coupled to this physics. And the descriptions of these physics are provided in separate modules as part of this course. Finally, the evaporation term, this one, the I dot, the rate of evaporation, is volumetric, and it's a function of position and time. So the expression for evaporation in the porous media is something like this, that has been used by quite a few of the researchers. And this, the origin and the details of this are described in a separate module. So that module, we need to go through that module to understand more about the I dot. But this is how I dot is calculated, and then it is plugged into the energy equation to bring in the evaporation, and therefore the heat equivalent of evaporation, which is lambda times I dot. In this final summary, we note that this is the heat equation that provides temperature at any location in the porous media. The temperature is shared by all phases, so everything, the solid, the liquid, the gas, at one point has the same temperature. The equation has terms like this storage term with a heat capacity that is volumetrically weighted over all the phases. Then the convective transport is by each phase, water, vapor, and air. And remember, transport includes a flow of the liquid as well as diffusive type movement of the, not just the liquid, the fluid. So flow of the fluid and diffusive type movement of the fluid as the case is, and thermal conduction, where the thermal conductivity is volume averaged over all the phases, and heat generation that comes from other physics. So either it has to be coupled with other physics, or it has to be known, and evaporation that has its own expressions, and it gets included in the heat equation with the latent heat. So it's the heat equivalent of evaporation. So all of these physics are together. So it's a very mechanistic way of describing the heat transport process. It's also a very comprehensive way to describe the heat transfer process. And the equation, when solved, gives that temperature at any position and time in the porous medium.